Okay? Yeah, you can go ahead and just sketch something in there. But let's talk about it. So here's the thing. Remember, this was just a prediction piece. Y'all have got some good ideas going. We do want to go back to what we did yesterday. So we're going to talk about some of these. So if I get you to move into the center of the room quickly. Okay? So let's move into the center of the room. Let's talk about these things and let's generate some ideas. So first things first, I want to talk about today. And yes, I did find the SD card. I don't know how I missed it. It was apparently sitting on my desk. And I don't know. Anyways, but we're recording today. Now, that means one, for all of our friends who are not here, if you have a friend who's not here, please make sure you reach out and say, hey, today was really important. Make sure you watch the video. Especially for those who weren't here yesterday. All today is building on everything we did yesterday. It's the same exact ideas, but we're building just a little bit. So make sure we engage in that. So we're going to come back to that prediction in a second. So we're going to construct polynomials through factors part 2. Going into what? What was yesterday's types of functions? We were building what? So remember we had 2 linear factors, right? And what did we build out of those 2 linear factors? A parabola, so it was a quadratic, right? Remember, we got to keep this in mind. What type of function is this? Linear, which is degree 1. We have another linear, which is degree, well, just this linear? So remember, y equals mx plus b, what is that exponent? 1, so it's degree 1. How else should we know, looking at this line, that it'd be degree 1? There's another thing to note. You and I talked about this earlier. Degree matches something. The number of roots, right? How many roots are there? 1. And? Right, so now when we dilate, remember we're multiplying which set of values? Which set of values are we multiplying? The outputs, right? We're dilating, we're multiplying those outputs. And so this is something a lot of y'all forgot here, but we want to, this is why we did this refresher. Ooh, that was a terrible line. Don't look at that vertical line. But if we're multiplying the outputs, all of these outputs are what? And all these are, and when I take a negative and I multiply it by a negative, what do I get? Positive. So all of these values for my dilated function are positive, okay? Then, remember I looked in between the zeros, right? And all of these values are, and what do I get when I do a positive times a negative? So all these values are. Now, why did we talked about this, why does it start to turn back up? It has to what? Which 2 points? The zeros. Remember, all of these values are what? Down here, they're negative. So to get back to 0, it's got to start to, there's an I word that we use in math. Increase, right? To get back, to go from a negative back up to 0, it's got to increase. And then after that 0, all of these are positive, all of these are positive. Positive times positive is. So remember, we're building quadratics. Because how many roots were there? 2. Right? We good with that? So 2 roots, okay? So those are the quadratics that we were building yesterday. And I want to build on, and so now today we're taking it beyond that, talking about cubics and something called multiplicity. Super, super easy. We're going to go to the textbook lesson that you tore out and just use that to support what we're doing. Because remember, I told y'all the textbook stuff was just hard for students to digest in the past. And so I found that this Desmos activity that I created helps a little bit, but we're still going to look at how they are related. First things first, no reflection this week, obviously. Didn't give you one, just because it's been such a short week. We'll start back with the reflections on next week. Today is also Friday. I forgot to ask yesterday, and it's been a short week. Does anyone want to do a Hero Friday today? I know, nobody's here. We're like, I don't know what's going on. Any ideas? Nobody? We scared? Oh, you're trying to get Kyron to do it? Okay, so you want to do it, Drake? Alright, I heard you want it. Are you going to volunteer somebody else?
Yeah, you want to volunteer.
You heard Kyron say he wanted to do
He
it?
said the other one they was working over there.
Oh, I did?
Yeah.
Yeah.
Oh, I don't remember
Your
seeing
hero
that.
was your dad.
What if I don't got one?
Is your dad not your hero, bro?
What if I don't got one?
Kyron, do
I
you have
never
one?
said that.
Hey,
Yeah.
alright, it's okay.
Right before you walked off the
Alright,
It's
Look.
crazy like both of y'all saying, how about y'all go up and do it?
that's what I'm saying. I will say this, I don't know if y'all remember this, but I did say, if you volunteer somebody else, that means you really, really want to go.
I didn't volunteer. You saw
Yes,
me.
you did.
I know you started to raise that man's hand, so you can go next week. Thanks. Alright. Since I figured that was going to be the case, I wanted to share a hero of mine that I haven't actually talked about as a hero, and I would say he's closer to a mentor than a hero. So, Mr. Javi actually knows this person pretty well.
Is it a mathematician?
No. I mean, he does a lot of math, but no, I would not consider him a mathematician. Did I not get a picture with him? I know I got pictures. Yes, you can turn the lights off. I need to find it. I wonder if it's just in my device. Let's see. What were the days I was gone last?
Wednesday, Thursday, and Friday.
Is that Alexa?
That was a while ago. There we go. It was back in September, right?
Yeah.
Yeah. All right, hold on. There we go. All right. So I don't know if you can see him very well. So when I was at the conference, I actually got to present with Dr. Zelkowski from UA. And so I don't know if I would call him a hero, but he's definitely been a mentor of mine. He's a big reason why I am the math teacher that I am today. So if you love the way I am as a math teacher, you can appreciate him for that. If you're a little frustrated, you can also appreciate him for that. This is the guy who took me from being a civil engineer into understanding how to teach math. I took a year when after I finished my civil engineering degree because I was not accepted into the University of Alabama's graduate program. I don't know what was going on. I think it was honestly the providence of God that they didn't accept me so I could get a year of teaching before I started. But there was just some wonkiness going on. However, Dr. Zelkowski is the head of the math education department at UA, secondary math ed, I should say. And so he has given me, or helped me have a lot of opportunities. He and I are working on a scholarly paper on a lesson actually that I'm going to use later this semester with y'all. That's all about using real world data to understand inverse functions. He used me to do this presentation about a program I'm in with him right now. He's nominated me for several awards, and so he's just, I've learned a ton from him, and I really appreciate him for that. So you've heard about my parents. My parents obviously really big deal. I think I talked about Coach Colvin. He was my cross-country coach in high school. Very, very formative for my life. And then Dr. Zelkowski has really, really helped me become a better teacher. So I really appreciate him for that. So that's my Hero Friday. I'm really excited to hear about Drake's next week. Thanks. I appreciate that. Mr. Kenny. What?
You for real now.
Really quickly, okay. Hey, so I will say this. A few of us apparently missed the memo. Yeah, you can turn that on. Missed the memo that Wednesday was an e-learning day and we were supposed to do an assignment. Quite a few of us started it. I know that the sophomores, y'all were actually taking the pre-ACT, so y'all didn't really have an e-learning day, but I do need you to complete this assignment before Monday. For those of y'all who did not complete the e-learning day assignment, then you have until Monday to earn up to 80% credit. You will have a grade for it. If you already completed it, you're good, okay? I'm going to cover a couple of things, though, to help y'all, because I know there's one difficulty. I think, if I'm being fair, that right here, the exploring and analyzing patterns, comparing familiar function representations, went like that. It was like 15 minutes total, I think, for most people. Not bad at all, because it was literally just linear and exponential and quadratic functions. Everything we've studied, a little bit of a review in there. But identifying key characteristics of graphs of functions was a little bit more difficult for some people. And so I want to look at this really quickly with you. This is literally an Algebra 1 review So it is really important. And I think overall, most of this was pretty easy. By the way, I would get out my notes page on the very first set of notes pages I gave you for this unit, because we're going to talk about one of those key concepts on there. I am going to do it more as direct instruction because it is stuff you've already done. Yes, so we're going to talk, that's what we're going to talk about really quickly. I'm going to memorize this so I can come back to it later, but I got to erase it, sorry. You look wonky. Boom, roasted. All right. So, got me. All right. So, whether you know what type of function this is or not, this is called an absolute value function. Hopefully we studied this in Algebra 1. May not have, that's okay. But, and they don't even tell you what the equation is, because you really don't need it to talk about these things over here. Now, select the number of y-intercepts. I think we know how many y-intercepts are, right? Like if I look at it, how many y-intercepts are there? There's one, okay? So that was probably an easier part for most students. One y-intercept, it says select the point, and so, boop, there's my y-intercept, done. Now, the number of x-intercepts, how many x-intercepts are there? 0, okay, cool. And does the function have a minimum x value? So this is where some people I think started to run into some difficulty, but look at the graph, okay? When we talk about x, which direction is it? Left or right, okay? Does it ever quit going to the left? No. It doesn't have an arrow down here, but there's not a stopping point. So the implication is that it's still going down and to the left. So does it have a minimum x value? No, okay. Got it right? By the way, don't forget, when you use Mathia, you can get hints and things to help you. You can, when you get things wrong, it'll give you hints. Use that for learning purposes. Now, it asks for a maximum x value. Does it have a maximum x? No, it keeps going down into the right. Okay, so a maximum x value? No. Now, it talks about domain here. That word look familiar? Okay, so when we say domain, what do we mean? What do we mean by domain? All the what? But like, we're not necessarily just this function. Any function ever, when we say domain, what do we mean? Oh, yeah, we need to write this down because this is a foundation piece on that proficiency scale. Any guesses? It will be negative infinity to infinity. We're going to talk about it in a second, but it is the set of all blank values. Which values for domain? X values. That's it. When we say domain, we are talking about X values. Okay? When we are talking about domain, we're talking about all those X values. So remember, I was saying I would write this on the back. It doesn't really fit anywhere on the front. I was saying I would put it on the back of those notes because it is a part of this unit, but not something I made a notes page for yet. Okay, so the domain is a set of all X values. Now, there are two main ways that we identify what the domain is. I'm going to show you first the way I recommend, and then I'm going to show you the way that they're wanting it on Mathia. The first way is what Miles was referring to earlier, and that most teachers here teach, called interval notation. In interval notation, you identify the minimum, you identify the maximum, and then you simply put a comma in between to indicate it's everything in between. So what was the minimum x value again? It never stopped, right? So the minimum x was negative infinity. And what was the maximum x? Positive infinity. So minimum x, maximum x. And then what does that comma indicate? everything in between. It's called interval notation because it is the entire interval from negative infinity to positive infinity. Hopefully that sounds familiar from last year. We heard that? Okay. That's mainly why I'm willing to do this as a little bit of direct instruction here. Does anyone remember what I need to still put here? There's parentheses or brackets. What's the difference?
I forgot.
We only use brackets
When it's closed.
positive or colon. We don't use it on, in.
So I will agree you don't ever use it on infinities. Because when can you use a bracket? When you can equal the value. Okay? So when that function can equal or actually have that value. Can you ever, or can that function ever equal infinity? No. So what do we have to use? Parentheses. It can never get to infinity, because remember that's the idea of keeping going for forever. So Leo, you're right, when it's infinity, I can never use brackets, but it's more because a bracket means that value is equaled or included, is the proper term there, that's included. Right, Mr. Javi? That's included, which means you can the function equals it, okay? And then we have a set notation that uses an inequalities usually to tell us the same information. Okay? However, in this case, if it goes from negative infinity to infinity, right? So let me click on this box here, statement to describe the domain. What statement says it's every real number? The domain is all real numbers. So when we have an interval notation like this, we can also say that it is the set, and we use technically curly brackets, they don't have that up there, but the set of all real numbers. There's other ways I would really write it, and that's more why they don't have the curly brackets, but that's essentially what it's saying. It's the set of all real numbers. Those curly brackets literally just mean set. Those curly brackets just mean set. Have you ever seen it written as words like that inside of the set notation, Mr. Hodge?
No, I just see it as all reals.
Yeah. We're just using the R, right? But that's what that says.
Right.
Yeah. I wish they just use interval notation. They do it later for other things, just not here, which is goofy. Okay? So the domain is all real numbers. Does the function have a minimum y value? No. What does it keep doing? It keeps going down. So no minimum y value. Does it have a maximum y value? Yes, it stops at some point. So we're going to select a point and stops going up right here. So you got to remember to start separating it from horizontal from vertical, right? Horizontal is my x or the, starts with a D, domain, whereas the vertical is going to be my y or range, okay? So what's that maximum y value? Was it negative 10? Okay, cool. Negative 10 is over there. Alright, and then so it says select a statement to describe the range. Now if that has a maximum, is it all real numbers? No, it is a subset. Now it wants us to write an inequality or an equation for that range. Now, so when we say domain, it's the set of all x values. When we say range, it's the set of all what? Y values. You tell them. Okay? The set of all y values. Hey, how about you? We'll focus on learning. Alright. So what is my, and I will point this out, I need y'all to be careful about this because students mess this small detail up all the time. What always has to go first in interval notation? That's minimum. Notice, we're talking about which set of values? Y values. And you always do a minimum, then a maximum. You've got to train yourself to focus on what is the smallest value, the minimum value first. And I know it's a small detail, but it's really, really, really important. So, it never quit going down, so what's my minimum Y value? Negative infinity. Bracket or parenthesis? Huh? Hey, have you ever gotten to a negative infinity? Can you get to negative infinity? I know Buzz Lightyear's like, oh, it's infinity and beyond, but can you actually do that? I don't think so. So can we use a bracket if we cannot equal it, or the function cannot equal it? No. So we use a parenthesis. By the way, you will hear me say parenthesis because parentheses is plural, parenthesis is singular. It's from a Latin root. I'm not going to sweat it if you don't say that, but it's just an is instead of an es. Parenthesis there, because notice how many of those do I have? One. What's the maximum y value? Negative 10. So minimum y, and then the maximum y is negative 10. Now, does that function actually get to that negative 10?
Yes.
So what do we need? A bracket. And that's why, again, I said parenthesis, because I have one of them and then I have a bracket for the other one, right? The value of negative 10 is actually included. There is a point at negative 10. So we're going to put a bracket there. If that value is actually there, if it gets there, if it equals the value, then we use a bracket. So, set notation wise, and they don't have you do the full set notation, but it's the set of y such that, that's how we read it, don't sweat that a ton, we just need the inequality. But what would be my inequality for y? Because this is where students usually have the most trouble. We have a negative 10, but is it just negative 10? All the way down to negative infinity. So it's negative 10 or what? Think about your inequalities. It's less than negative 10, isn't it? Or it can what? So y is less than or equal to negative 10. This is all that Mathia is looking for. Y is less than or equal to negative 10. There you go. By the way, I will point this out. If I were to do this, one, I would practice with interval notation, but two, write out the interval notation and then use that to write your inequality. Quite literally, negative 10 is the maximum, and it's everything that is under it or less than it, right? So literally, y is less than or equal to negative 10. That's just how I would write it. Okay. There's lots of ways to do it. Hopefully that's a good little refresh on domain and range. What are your questions before we continue? David's like, Mr. Kenny, I'm killing it. I'm ready. Questions, comments, concerns? Okay, so this unit and every unit here on out, we're going to be using domain and range and building on domain and range for something called domain intervals of increase and decrease, focusing on maximum and minimum, relative max, relative min, things like that. So we want to make sure we learn this well. Mathia will help us do that. It is a quick little refresher. Okay? Huh? What's in December? What subject? Domain intervals of increase and decrease? That's next unit, baby. It's not bad. I want you to think about this right here. If you look at this curve on this section, remember we moved from left to right, is it increasing or decreasing? Remember, if we're moving this way,
Oh wait, which one do you want?
this one right here. If I'm moving this way, what's it doing? Follow my finger. Is it going up or down? It's going down, so what's it doing? Decreasing. If I think about a tangent line here, just touching at one point, that slope is negative, right? That means it's decreasing. So I would just identify the domain where it's decreasing. That's it. If I look over here, what's it doing? Increasing. Notice if I draw a tangent line, is that slope positive or negative? And so what's it doing? Increasing. And Mr. Hobby can attest to this. You learn this concept now, it's going to help you a whole lot in calculus if you take calculus. It'll help you, period, but if you take calculus, which is a beautiful subject, everyone should take it. Not really, because not everyone needs it. It's not bad. Listen, calculus is really fun. Not everyone needs it in everyday life, but it is fun.
I think it has a organization.
That's what I like to hear. That's what I'm talking about.
Statistics would be a lot. I like.
It's more helpful.
Then take it. I hear,
I just
listen.
don't know about like normal distribution because sometimes I go into statistics.
Yeah, but if you've already had some background with it, that would help you a whole lot, right?
I'm about to take a stat my senior year.
What's this?
There's no math you have to take. After Algebra 2, you can take pre-calculus, you can take AP Statistics. After pre-calculus, you can take AP Calculus.
God. Gorgeous.
Wait, all like,
She's great.
12th grade here.
Yeah, and then there's also dual enrollment stuff.
We're doing a little calculus.
Calculus, yeah.
A lot of stuff.
Alright,
Really?
sorry, we gotta continue though. We got our math to learn. We can talk more about that stuff in the future. So we gotta get back to these things, we gotta get back to the bell ringer. As a quick point of order, these are our proficiency scales. These again are the concepts. Hopefully that foundation, we're all good to go from last unit, right? Identifying zeros in factored form by applying the what property? Zero product property. That's why I focused on it so much last unit. Determine if a polynomial in standard form and in factored form are equivalent. Remember Jaden talked about that yesterday and last week. How do we know if they're equivalent? What can we do?
You insert it.
What, oh, I need better language than that. Is Jaden the only one who knows this?
Probably.
Whew, it's hurt my heart. Didn't teach this. Oh, no. Come on, guys. Like if I were to graph two functions, and that's what I'm trying to get you to see or think about. If I were to graph two functions, would these be equivalent?
No.
Why not? They don't line up. What's that more mathematical term we use? It's not just the roots. There's an M word that I used every time. They don't map to each other, right? They're two different functions. These two, though, would they be equivalent?
Yes.
Because they map to each other. It's not just about the roots. This input would have the same. 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 So when they map to each other, even though the equations may look different, the same inputs are mapping to the same outputs. Right, there we go. Okay. That's equivalence. Woo. So we're all going to crush that tomorrow, right? Or Monday. It's not just going to be Jaden who goes, oh, Mr. Kinney, I can... He doesn't sound like that. Mr. Kinney, we can map graph them and map them. All right. Zero product property, zeros, factors. Hopefully that all sounds familiar. We started on this yesterday. Sketching polynomials, quadratics and cubics when given the graphs of their factors. Sketching polynomials when just given the factored form of the polynomial or when asked to dilate a polynomial by a new factor. And finally, determining if the y values of a polynomial are positive, zero, or negative based on the graphs of their factors. All of those are super heavily related. I'm going to continue into those. Alrighty then. That's not what I need. That's later. So let's look at the bell ringer. It's only been 40 minutes. Just now getting back to it. It's fine. I don't know why it makes me approve it, because I set it up so that you can get in without me having to approve, but... Alright, so, let's look here. That's not what I want. That's what I want. Okay, so I'm going to focus on a couple of details. So, we had different responses around the room. One of the things I want to talk about that I saw a group talking about... Actually, let's start here. At first, quite a few of us noted these 2 points here. Why those 2 points?
Because they're zeros.
Those are zeros. And tell me this, what happens when I multiply by a zero? I get a zero, right? We're multiplying these three linear factors. We're going to get a zero. But are those the only two that I want to note?
No.
What else?
Duh.
There's another zero, right? Everywhere there's a zero, I want a zero, right?
Yeah.
Hey, by the way, did anyone actually sketch this out on the iPad? Y'all did, didn't you? So let's pull that up. Okay, that's okay. That's a great screen.
Well, we got.
Yeah, the 8's the 2. Okay, oh, and the 8's the 2. So here we go, right? Notice we got some notation on here. Notice they marked it. It's not the prettiest, but also it's on an iPad. That's okay. We do want to do a couple of things really a little bit better, because I will point this out. Is this a function right now?
It technically could, but it don't matter.
I was saying, it doesn't matter that vertical line test. And it's okay, but on assessments, keep in mind, I want to make sure that it's a function. Be careful. Again, it's an iPad. It's wonky. I get it. Okay, so they marked their inputs or their x-intercepts, and they made sure they went through it. Now, remember, I showed this yesterday. What did I draw with them as a hint before I left? That vertical dashed line. It just helps me visualize. Like that's the whole reason. It helps me visualize where things can change. Because notice right here, this green linear function goes from being, what are these values?
Negative.
To positive, okay? So that's where a transition can happen, okay? But we mark these zeros. This is the prediction that we got. And so I know when I was talking to the group of 8s, they wrote a quick note. And so this is kind of what we saw, something like this, from a couple of different groups. Very similar to what they have. What they have is fine, especially for now. We're going to explore it more later. But Leah, what did you call this at first? Not what you have written on the board now. What did you call this originally?
It wasn't her, it was me.
Oh, Crystal, what did you call it?
2 parabolas.
2 parabolas! Does it kind of look like 2 parabolas?
Yeah. Yes, well, yeah.
Kind of.
But I want to point this out. That's continuous. I never picked up my marker, did I? So how many functions is it? It's just one. Okay. So what did we talk about? What did we call this?
Cubic,
A cubic. Why?
because it's 3 zeros.
There's 3 roots. There's 3 zeros. So what's the degree?
3.
Okay, so it's not 3 degrees. It's just degree 3. So it's got to be. Notice another way to read this. X cubed. So cubic. And so we're seeing early here. We're going to build on this in a minute. How can we construct a cubic function? What did we use here to construct that cubic function? 3 linear. Now, be careful. Is it an equation here? No, but it is 3 linear functions, right? We just have the graphs of them now. We can use equations later, and we will later. Because I can actually look at this, and I could say, hey, you know what? This function is y equals, I think that's negative, it's negative x plus 2. The green one is y equals 2x plus 4. And the blue is 1/2 x plus minus 3. And so literally, I am multiplying those expressions together, right? It's just I didn't have those expressions yet. It would be this. We'll do more of this later. You don't have to know all that. I'm just trying to build on what Elizabeth said. Okay. So we have those ideas. We're building off of those zeros. And it is a cubic, x cubed, because we had how many zeros? 3, right? So we had a couple others make the similar prediction. Crystalline, right? Same idea. And we're going to talk more about how to get that shape instead of maybe another shape, because there's a few options. And so here's what I want us to pick up on. So the question is, what type of function is created by 3 linear factors? How can you determine what the dilated function looks like using the linear factors? Now, the prediction y'all just made was that it's going to look like this and it's going to look like a cubic. Is that right? Mm-hmm. But did we look at lots of cases or just one case?
One.
So that's a prediction. We need to test that prediction. Math is not just, hey, I see one thing and I'm going off of that. It's, hey, I see a thing. I'm going to make a prediction about that thing. Now I got to test it. I need to test it heavily. So I want you to work within your small group. I want you to go to your vertical surfaces with the iPads, test it out, come up with some predictions. Once you feel like you have a firm prediction, write that on the board and move on, right? Don't wait for me to bring us all back together. You just have to have a prediction. It doesn't have to be perfect. Keep it going. 3, 2, 1, go!
Okay.
Thanks, guys. I appreciate you.
Can I write something?
Especially you, David. Yes.
Me?
Yeah, I said especially you. I appreciate you. Should I not appreciate you? Should I be upset with you?
No.
Oh, okay.
I didn't say anything.
That's what it sounded like. Y'all to come to the center of the room and let's debrief. I'm going to give you time to make some notes about this, so I want to spend about 4 or 5 minutes. Listen, y'all are making fantastic sense of a few of these things for sure, but I want to point out one of my favorite things that I saw a group do that can be really, really, really powerful. Actually, I want to start over here. I want to talk about this special case. Most of us did eventually notice this special case. It would help if I knew where my chalk was.
Oh.
Look, Mr. Javi, I got purple chalk.
Nice.
I'm excited. All right, so listen. Most of us noticed when we were multiplying 3 linear factors, what type of function were we supposed to get? So we normally got a cubic, right? But there was a special case that several of us noticed when our slope here was 0. Because what's 0 times anything? And so does anyone remember the name of this type of function if y is always -2? It's always -2 or it is constantly -2? This is a constant function. And in this case, which we didn't get that graphed up here, let me just do a quick sketch of an example like this. So boop, bop, and
Bam.
boom! Okay, or bam, that's fine. Alright, so in this case, I want y'all to look at that, right? When I look at this, those 3 linear factors have how many roots? How many roots do these 3 linear factors have? They got 2, right? So when I dilate or multiply these functions, how many roots is that function going to have? 2. Now, Will points out, this is important to notice, like my dilated here would only be degree 2 because this linear has degree what? 1. This one is degree 1, and this one's degree 0, right? So we talked about that in a few groups, and so that's why when we multiply, we only get 2 zeros or degree 2. And so again, though, the same things we've been doing hold true. Remember, you don't have to draw this line, but it helps you look at the different regions. I talked about this with Drake's group. I look at one region at a time. I don't jump regions. I look at one region at a time. In this region, these values are negative. These values are, and these values are negative. Even though I can't actually see it, it continues, right? And when I multiply 3 negatives, I get a negative, so that's 0. Now, based on the patterning we've seen, we would expect it to go then positive, and then negative through there. Notice, I didn't even take the time to look at the rest. I was able to find it from just one. But we can check it. What's a positive times a negative times a negative? Positive times negative times negative. That's positive, right? So notice all those are positive until we get to 0, and then it goes to negative. But I want y'all to see something over here that I would take a note of 1,000%. My bad for bumping into you, Kennedy. All right, right here. Beautiful. Color coding. Like, this is something that I usually have to wait a few days to point out to groups. But this is what I would do. This right here, if I was to see this on assessment, would that be pretty strong evidence of where we're getting our positives and negatives from? Notice they color-coded. I can clearly see every time I have pink, which by the way, you have markers in your boxes, right? You have colored pencils in those boxes. I can clearly see every time there's pink, those values are what? Positive. All these are positive. And I can also tell from here why they know it's positive. Now, you could put the negative and the positive, but I like this. So negative times positive is positive. And then down here into the blue, they are negative. And they even use a third color to mark the what? Zeros, the roots. And so we want to notice, right, that that's a really powerful way to show evidence of understanding. Marking those roots or zeros in a color, then marking our factors, and showing how we're getting those positives and negatives. I'm not going to dwell on this a ton because we did this. What questions do you need to ask before I continue on for this discussion, though? Because I heard everyone talking about this. Does that make sense? I just want to celebrate this because this is a beautiful way to show evidence of understanding. We good? And so once again, when we have 3 linear factors, each of those is degree. Each linear is degree 1 with how many zeros?
1.
Right? And so in total, we would have a degree 3 with 3 zeros. And then we moved to this one. And so what was different about this one on this slide? What do we have going on here?
Quadratic.
A quadratic and a linear, right? And so how many zeros did that quadratic have? 2, and its degree, the quadratic, is degree 2. And we dilated it by this linear, which is degree 1 with 1 0. And so how many zeros did we get? 3. So I need to point this out. How can you construct a cubic? What can you do?
3 linears or quadratic and linear.
How to construct a cubic? You can do 3 linears. That would give you 3 zeros or 3 roots, right? or a quadratic and a linear. Guys, that's huge to notice. That's how we can construct those cubic functions, is we can do a quadratic times a linear or 3 linear factors. And so that's what a lot of us started to notice here. The cubic is created when you do quadratic times linear functions. So does it change, though, how I figure out what the cubic is going to look like? This linear has what type of values? Positive. The quadratic has?
Positive.
And a positive times a positive is?
Positive.
Positive. Positive times a negative is? So that doesn't change. Guys, it doesn't matter how complicated the functions get. It doesn't matter what degree we get to. That concept holds true. The places that it can change is at these what? These roots or these zeros. But does it always change? I don't know that everyone got here, but I want y'all to see something. If we go to slide, which we did pretty well here, so I'm going to skip it for now. I want to talk about slide 6. I asked you on this slide to construct a polynomial when it has the same zero, or the same, the same root. So let's try to do that really quickly. Nope, that's definitely not it. There we go. So, Malia, can you hit the lights for me real quick? What is different? I'm going to ask the jacks up here about this. What did we talk about is different when we have the same x-intercept?
It doesn't go through it, it bounces back up.
So normally, hasn't our cubics gone through the x-axis here? See how it goes from positive to negative? It goes through. But what happened here when it was what we call a double root, or the same root? It bounces. Think about it like a basketball. It touches and it... So when we have a double root, it bounces. When it's a single root, what does it do? Goes through. And I know y'all need to, we gotta take a picture of this. One last thing I want to point out, that's going to wrap us up, is this. What if we had all the same roots? What happens when it's all the same root? It goes, does it bounce again? When we have a triple root, 3 roots, the same, does it bounce? No, what does it do? It goes through it again. Any guesses what's going to happen when you have 4 roots? It's going to bounce. And so we're going to play with this some more, but I need y'all to make sure that you take these notes about the, by the way, I mentioned this earlier. Hey guys, really quickly. Hey, you see how these roots are the same, or it's multiples? That's what we call multiplicity. This double root, that is a root with a multiplicity of what? Any guesses? Predictions?
2.
Multiplicity of 2.
Let me put this
A
on the
single root is a multiplicity of 1.
Let's put this on the one that says multiplicity in standard form.
Leave that alone for now. Yeah, so this is actually on the original Frere model that I gave you. There's a section about multiplicity there. Multiplicity and behavior around each root. That's where I would add that information. Hey, don't worry about the practice yet. We'll do some of that on Monday, especially for those of y'all that were not here. Unless you want to go ahead and get a little bit of practice in. Study these ideas. Please review them. Prepare to teach your classmates. But we are not, you don't need to do the practice yet. Thank y'all for a great short week. Don't forget, you're always capable of more.
For how good we